So hello and welcome to the first video for statistics in research and ethics. Statistics, just the name of it, makes people sort of cringe or run away in fear sometimes. So the first thing that we will do is tackle some of those preconceptions. So what are these preconceptions based on? Well, I think a lot of people, when they think of statistics, this sort of stuff comes to mind. A field that's full of numbers, full of formulas. You get introduced to these formulas and processes first, and then sort of built up and maybe promise something interesting at the end. And then certainly even in my undergraduate degree, I was doing a minor in psychology, and the second year, first class, this was the statistics class that or sort of formula I was presented with straight away. And so I subsequently dropped out of that unit because, and in fact that minor in general, because it just did not seem what I wanted to be doing. But statistics is not actually that. I mean, that's one way of teaching it, sort of building up and getting to the interesting questions last, but I think that it's actually should be interesting from the start. So as I continued on and got interested in some particular questions in exercise science, I ended up having to design some experiments, collect some data, and then I was presented with this, and this is some data that we've collected in class this semester, where we were interested in looking at simple reaction times using your dominant hand and non-dominant hand. So an online sort of reaction time tool, and we use dominant hand, and we use the same participants to do non-dominant hand, and we got this data. And this is really interesting because you look at it and you think, oh, well, it's a little quicker for that person for dominant hand, and maybe the next person, but then different for this person, and is it big or a little difference? I'm not really sure. So that there's all these questions, and we can't really go any further without statistics. So statistics is really that tool that we use to answer interesting questions, and as we have answer interesting questions in interesting ways, statistics becomes really interesting and doesn't need to be super complicated or difficult, and that's the way that we're going to cover it this semester. So we're going to try and tackle it from that perspective of interesting questions. So when we're thinking about how statistics can help us answer these questions, it's kind of helpful to actually be able to break that into a couple of different ways of how we do it. So you'll hear us this semester talking about two general types of statistics, and then we'll sort of might break them down a little bit further. So those general types are descriptive statistics and inferential statistics. And descriptive statistics in particular just describe a situation the way it is, and inferential statistics infer a little bit more, are trying to get some sort of further result. And we'll start with descriptive statistics, but I want to give you some examples of how we might see both of these in research to start with. So this one's a really interesting case of descriptive statistics in play. So it's looking at the epidemiology of weight training related injuries presenting at US emergency departments. So any injuries that were presented from free weight activities, whether they be in a gym or home gyms, presenting to a large number of US emergency departments over that period of time. And you can see from the table here the sort of numbers they've got. So you can see, thousands and thousands of presented cases to emergency wards, and you've got your actual counts from a smaller sample, and then national estimates based on that. So they're sort of expanding or extrapolating from what they have in particular areas. And so it doesn't do anything beyond just present these numbers, but these numbers are kind of interesting enough. So if you sort of look down at the injury diagnosis section, you can see that almost half of the injuries presented are sprains and strains, and then the hemorrhages are 0.1, so there's much less hemorrhages than there is sprains and strains. You can see what happened to those people down the bottom. So 98.2% of those people were released. So most of them are fairly minor, we find out. And there is a small number that might have been hospitalized, and no fatalities from that particular group as well. So this is interesting enough, but that's as far as this study goes. It's descriptive in nature. So here's another interesting example of descriptive statistics in exercise science, and this study in particular was interested in looking at why people take up cycling as a physical activity. So they distributed an online survey out to 10,000 members of Bicycle Victoria, and they got responses from a little over 2,400 of them. And as you can see from the data, there's some interesting results. So you can see that if they've tried to condense the reasons into a few different categories there, and you can see the largest responses, or the most common responses, was to do with health and fitness, building physical activity, and the least common responses was to do with relaxation and stress reduction. So those previous examples, while they were interesting, they were kind of pretty basic from a statistical end. They were just really capturing a whole bunch of data, and they were reporting that in a fairly raw format. So using averages or other central tendencies, or they might have been using frequencies or number of people who fell into a particular category. So that can really be quite insightful, that research, but it's not inferring any other conclusions from your results. And there is a whole category of statistics that help us infer more from our data, and they're called inferential statistics, as in infer more. And so an example of that is this research here, and the researchers in particular here were interested in looking at the effect of sodium bicarbonate or baking powder on an activity that is high intensity and therefore is influenced by potentially by blood lactate threshold. And so it's a common anecdotal claim that this sodium bicarbonate, if you ingest it, and I wouldn't recommend it, it actually can cause sort of severe problems, but if you ingest some of it before, it can actually help to buffer your blood lactate. And so these researchers are interested in inferring, or collecting some data and inferring some results on the effectiveness of this treatment. So they implemented this. They gave one group a placebo, they gave one group the sodium bicarbonate, and they got them doing Wingate tests on 3 sort of occasions with some rest in between. And you can see the blood lactate climbing across those 3 tests. And then if you look closely, you can see the different conditions there and the differences between those. And so we'll cover exactly what's going on in this inferential statistics in further modules, but that they're using similar sort of data as we saw in the descriptive, but then they're trying to go a step further and seeing if these differences are actually meaningful. So there's a whole range of those types of comparisons that we can make, but there's a whole different sort of range of inferential statistics. And again, we'll cover more of this in later videos, but another example of inferential statistics might be something like this study. And this is not a real life study, but this is a sort of a suggested question where we might be interested in oxygen consumption, so our VO2 and the speed in a 10,000 meter run. And if we think of that average oxygen consumption and how it might relate to average velocity, you'd probably expect to see a graph that looks a little bit like this, where you plot the two together. Each dot is one individual, and those who had a higher average oxygen consumption during the race also had a higher velocity. And so you start to see a relationship going on, and that relationship is inferring something from the data that's beyond just reporting basic descriptive statistics. So hopefully that gives you some nice examples of how descriptive and inferential statistics might look like in exercise science. So then we're now going to go into, or delve further into, using the first one that we mentioned, descriptive statistics. And it might seem very simple. Most of us have used averages before and frequencies, so just a number of things occurring sounds pretty simple. But we might want to take a step back first and think about how we actually go from the variables that we talked about in previous modules into measures, because it's a bit more complex than we think. Take, for example, the tennis serve that we talked about when we introduced variables. In general, we started thinking, well, from this situation, the tennis serve, there's things that we can measure like racket head speed and elbow flexion and heart rate and gender and shoe type and age and weather and many more. So there's so many things that we could measure in this situation. But if you think closely about it, we can't really treat all these the same. So we're going to get a number if we measure racket head speed, for example. But if we measure gender, then it's just going to be in one of two different categories. So we can't really run an average on that. So how do we then think about these different variables? In its most basic form, we can think of variables or anything that we can measure in fitting into 3 scales of measurement. So nominal, ordinal, and continuous. So what's a nominal measurement? Well, I've got think name up there, and so it's a good one to think anything that you can categorize but doesn't necessarily have a number or even an order. So for example, gender is something that we can measure, we can classify people into male and female, we can compare, and we can even run frequencies of how many males or females that we might have in a particular research piece, but it's not something that is then has an order or a number to it. So it's a nominal measure and has its own characteristics. Same thing with something like an experimental group in a study, where we might give one group a resistance training, we might give one group no training, and so their measure would be a nominal measure there. And this is what nominal measures look like if we were to sort of write them down. Even on an Excel file, we might sort of have a column there where the participants got an identifier, and then next to them we've got their measure, whether they're male or female, or whether they're in the resistance group or whether in the control group. And the most common way we use these nominal measurements are to categorize for comparison. So they quite often end up being our independent variables in research. The second scale of measurement is the ordinal measures, and so I've got up there think order, because these we classify like nominal measurements, but they have some sort of order to them, and they might even appear in numeric form, but there's something quite special about them that separates them from other numbers that we might measure. So say for example we have a sprinting study where we might want to get sort of a group of sprinters and put them in a large race, and then we rank them on their race positions. So we've got someone who finished first, second, third, fourth, so we compare that race position that they finished with the amount of hours that they've trained in the last 5 years, for example. And so that the position that they finished in the race is going to come with a number, but that number, quite importantly, doesn't necessarily represent the proportion difference between people. So say for example we have our sprinter in the race who finishes first, and they finish say 4 seconds ahead of second place, and so there's quite a big distance between first and second, 4 seconds there. But then we have our second and third place where there's only half a second difference, and so whilst in our analysis first, second and third all have the same distance between them, in actuality in terms of time or velocity, then there's not an equal distance between those. So it's an order, but it doesn't have any discrepancies between how big each of those positions are. So we might have same thing, sort of baseball pitchers ranked on speed, and we might compare them on fast and slow. We might say there might be a questionnaire we give to a certain group and ask them how satisfied they are with training, and they might be high, medium or low, so they fit into one of those categories. It's an order, but there's no known difference between, or it's not measured the difference between those. So how would ordinal measures look when we write them down? Well, they look a little like this. So if you think about that sprint example that I gave you again, participants down the column on the left hand side there, and on the right hand side we have their finishing position. Same thing on the training satisfaction there, you can see high, medium, low. So the final scale of measurement that we use are continuous measures, and these are ones that maybe we're a little bit more used to and may form often our dependent variables in research as well. So where we use that sprinting example and the last one when they're ranked, we could also have a group of sprinters or runners, and we could time them over a particular event, and then when we use that time and have that related to how many hours they've been training, then we would start to see the discrepancies between someone who'd finished really far ahead and someone who'd come, the small difference between second and third. So it's more of a continuous ongoing measure, and a hallmark of it we see is decimal places. So we see decimal places in things like time, we see decimal places in things like temperature, and anything else we can measure that sort of we can see continuous intervals with, then it's going to be a continuous measurement. But these are two interesting examples I've given here because they're kind of a little bit different in an important way. So say for example the top one, if I run a race and I take 30 seconds and you run a race and you take 15 seconds, then you've run twice as quick as I have, or I've taken twice the time that you have. So it's sort of this ratio, and if someone else takes 60 seconds, they've taken twice as long as me. But in temperature, if it's 30 degrees outside, that's not twice as hot as 15 degrees, because 0 is just some arbitrary measure on a scale, whereas in the top one, 0 is an absence of any data. So this may sound trivial, but when we treat our data, when we do analysis, this actually becomes quite important. So we need to start using different terms for these different types of continuous measurement and what 0 means to them. So in the cases where there's an absolute 0, like in time of a particular event, it's known as a ratio continuous measurement. So movement time is an example, kilometers covered, both of those are things that if we get a 0, it means there's no data. Whereas if 0 is an arbitrary number on some scale, then we start calling them interval continuous measures. And so those are things like temperature or say trunk twist. So in biomechanics, we might measure someone's trunk position when they land on the ground, and if that's 0, well, that's just an arbitrary point. 10 degrees is not twice as much as 5 degrees, it's just a different point on the scale. So that's an interval continuous measurement. So what do these continuous measurements look like when we write them down? Well, pretty familiar with them, I think. So here's what they look like. The kilometers covered, for example, on the left-hand side, we can see participants running down the first column, and then the second column, we can see our data, and it's got decimal places there. And then trunk twist, for example, on the right-hand side, we can see our data there and the decimal places, and we can even see some negatives in there as well. And so these are the 3 scales of measures that we can have, and once we understand those, we can sort of move on to how then we might use measures of things like central tendency or variation, and then eventually on to inferential statistics.